Now we have several exercises. So some of the exercises I will explain, and some of the exercises I will left for your exercise. Now consider the sequence xn in the usual metric space Q. Okay, where the terms of the sequence are x1 is equal to 0.1, x2 is equal to 0.1, 0.101, x3 is equal to 0.0101001, and x4 and so on. Okay, and then prove that xn is a Cauchy sequence which does not converge to a point of Q. Now you have to see. Okay, this if you look at as x3, x4, or you go in this way x4 or x5. So the difference with respect to the usual metric is very, very small. It means that they are so you can see that very easily that xn is a Cauchy sequence, but it is not converging. You will have to check to which point this sequence is converging, and that point is the irrational number, not in Q. So this sequence will not converge. So you will have to find out the converging point of this sequence, as we have seen in the case of this one. Okay, here is converges to under root 2. What will happen for this? Okay, check. Prove that next exercise is prove that every Cauchy sequence in a discrete metric space is convergent. Okay, very nice. Every Cauchy sequence in a discrete metric space is convergent. So let's say here is let xd be a discrete metric space and xn be a Cauchy sequence. Okay, and now let us recall the definition of the discrete metric. So dxy is 0 when x is equal to y, and it is equal to 1 when x is not equal to y. Then let epsilon is equal to 1 over 2. And now since xn is a Cauchy sequence, then there exists a positive integer n such that xn is less than 1 over 2 for all mn is greater than n. Okay, it means what? It means that from the definition of the discrete metric D, so this is less than 1 over 2. 1 over 2 means the value of this can be 1 or 0. Okay, but this distance is strictly less than 1 over 2. So that this must be 0. And this must be 0. It means that the xn must be equal to xm. So xn must be equal to xm for all mn is greater than 1. So it means that after some time, after this capital N, okay, the terms of the sequences are repeating. So if they are, so that is to say, in other words, xn is of the form x1, x2 and x capital N. Okay, because all other terms after this capital N, all terms are same. So suppose these are x, so this is xxx. So this is what? This is your eventually constant sequence. Okay, so eventually constant sequence, and therefore the sequence, this sequence converges to x. So this sequence converges to x. Now next is prove that every Cauchy sequence in a metric space is bounded. Okay, so this you can prove very easily, as we have proved that every convergent sequence is bounded. Every convergent sequence is bounded. Every convergent sequence is bounded. Okay. So another exercise is that let D prime be two matrices on the same metric underline set X, and there exist two real numbers alpha 1 alpha 2 greater than 0 such that alpha 1 dxy is less than or equal to d star. Okay, so this is d star xy is less than or equal to alpha 2 dxy. Okay, then prove that the sequence xn is Cauchy. Okay, in xd. In other words, the sequence xn is Cauchy with respect to the matrix D if and only if it is a Cauchy sequence with respect to the matrix D star. Okay, keep in mind D and D star satisfying this inequality. So, if this inequality holds good, then if xn is a Cauchy sequence with respect to D, then it is a Cauchy sequence with respect to D star, and if xn is a convergent sequence with respect to D, then it is a convergent sequence with respect to D star and vice versa. So, this you can prove very easily. It is not very difficult. Just you take converging to this point and this point, and you will see that dxn is very simple. You can do. I hope you try. Otherwise, we can see later. Next exercise is let xn be a Cauchy sequence in a metric space xd and xnk be a subsequence of xn. Show that dxn xnk is equal to 0. Okay, it's very important. You see, this is the Cauchy sequence. Okay, so if you can take x and k is equal to m, so you will get the answer. Very simple way. But you can prove this one. So let epsilon is positive. We have to prove that this thing. So let epsilon is positive since xn is a Cauchy sequence in x. So there exists a positive integer n such that dxn xm is less than epsilon for all nm is greater than n minus 1. Okay, so for a while we can take m minus 1 just to make it proof. And now n, capital N, you take this one, okay, is greater than or equal to n, and n is strictly greater than n minus 1. And therefore, you can take this is equal to this n, okay. So here you can take m is equal to n capital N, and this is your n. So this is less than epsilon. So it means what? It means that here is you can see that the limit of this okay is equal to 0. So this way you can prove. The next exercise we say that let xn and yn be sequences in a metric space xd such that yn is Cauchy. Okay, yn is Cauchy and dxn yn converges to 0. Then prove that xn is a Cauchy sequence. Okay, very important, good exercise. Xn, yn are sequences. This is a Cauchy sequence, but this dxn, yn converges to 0. Then yxn is also Cauchy. Okay. The second thing is that if xn converges to 0, if fn converges to x, if and only if yn converges to x. Okay, let's see the proof. The proof is that so we have to prove that first xn is a Cauchy sequence. Keep in mind, we are assuming that yn is a Cauchy sequence and dxn yn approaches to 0 as x tends to infinity. So let epsilon greater than 0. Since yn is a Cauchy sequence, there exists a positive integer n1 such that dym yn is less than epsilon by 3 for all mn is greater than n1. Now dxn yn approaches to 0 as n tends to infinity. So here from this we can say that there exists a positive integer n2 such that 1 over n2 is less than epsilon by 2 and dxn yn is less than epsilon by 3 for all n is greater than n2. Okay. And then we can use the triangular inequality. So by the triangular inequality we can write dxm xn is less than or equal to dxm ym plus dym yn plus dyn xn. Okay. And so for all nm is greater than n2 we have dxm xn is less than, this term is less than epsilon by 2, this is same, and this is less than epsilon by 2. And now take n naught is equal to maximum of n1, n2. Then for all nm is greater than n naught, we have dxm x is less than epsilon by 3, this is less than epsilon by 3, this is less than epsilon by 3, so whole is equal to epsilon. And therefore, xn is a Cauchy sequence. So this way we can prove that. Now, for the B part, xn converges to x if and only if yn converges to y. So that you can prove. Take the triangle inequality, we have dyn x is less than or equal to dyn xn plus dxn yn. And now they take the limit, okay, as n tends to infinity, so we can write in this way. And then you see that because it is a Cauchy sequence, so this converges to 0, okay. And if xn converges to x, if xn converges to x, it means that this is equal to 0. If this is equal to 0, then yn converges to x. Then yn converges to x. So here you can prove yn converges to x. So that is the main result. So you can prove in this way. Okay. Now we have several other exercises. Some are again, as I mentioned, that I am giving the proof, but the best way is that you can try first by yourself. If you could not succeed, then you try to check the proof here. Okay, so just you see the proof, just you see the exercise. So the next exercise is that let xd be a metric space, okay, and xn be a sequence in x such that dxn xn plus 1 is less than 1 over 2 raised to the power n for all n. Okay, then prove that xn is a Cauchy sequence. Prove that xn is a Cauchy sequence. Actually, you see, we will use this result in several other in proof of several other results. So let epsilon is greater than 0 and choose a positive integer n such that 1 over 2 raised to the power n minus 1 is less than epsilon. Then for all n is greater than m is greater than or equal to n, we have dxm xn, okay, is less than dxm xm plus 1 plus dxm plus 1 xm plus 2 and so on, and dxn minus 1 xn. Okay, so the extension of the triangular inequality, by extension of the triangular inequality, we have this inequality. Now, because here you can see that xn plus 1, that is to say the distance between the consecutive two terms, okay, is less than 1 over n. Okay, if the first term is xn, so here is the first term is m, so it is 1 over 2m. Here is the first term is m plus 1, so it is 1 over 2m plus 1. Here is the first term is n minus 1, so it is 1 over 2n minus 1. Now we can write this in the summation form. So it is equal to, you start from k runs from 1 to infinity, 1 over 2 raised to the power k, which is equal to 1 over 2 raised to the power m minus 1, and which is less than, from here, okay, this is less than 1 over 2 raised to the power n minus 1, okay, and that's why we are choosing this is less than epsilon, so this is less than epsilon. It means what? It means that xn is a Cauchy sequence. So this way you can prove that xn is a Cauchy sequence. Now, take another exercise, and which is again a very simple exercise. So exercise is the following: let xn and yn be Cauchy sequences in a metric space xd. prove that this is a Cauchy sequence. That is to say, if xn and yn are Cauchy sequences in a metric space X, then dxn is a Cauchy sequence of real numbers. Okay? So this way you can see that as we have seen before, that for any mn, dxn minus dxm is less than or equal to dxn comma xm plus dyn comma yn. And since xn and yn are Cauchy sequence for any given epsilon positive, there exist positive integers n1, n2 such that for all mn is greater than or equal to n1, we have dxm xn is less than epsilon by 2, and for any mn greater than or equal to n2, we have dyn ym is less than epsilon by 2. And now you can set n is equal to the maximum of n1 and 2, and then we will see that for any mn is greater than or equal to n, we have from here this is less than epsilon by 2, this is less than epsilon by 2, the whole thing is less than epsilon, and therefore dxn yn is a Cauchy sequence of real numbers. So this implies that this is a Cauchy sequence in R. So these were the exercises related to the convergent and Cauchy sequences. Okay, we can have some more exercises, not too many, but some more. Suppose xd is a metric space, and you know that with the help of d, we can define another metric d star, okay, which is equal to the minimum of 1 and dxy. Then show that xn is a Cauchy sequence in the original set, yani the xn is a Cauchy sequence with respect to the metric d, if and only if it is a Cauchy sequence with respect to the new metric d star. Okay, so the question is show that xn is a Cauchy sequence in xn is a Cauchy sequence with respect to d if and only if it is a Cauchy sequence with respect to d star, and that you can, I think, prove very easily. So I left it for you, but I take another exercise where x is equal to C01 with the metric d2fg. d2fg is equal to the integral from 0 to 1 f of t minus g of t whole square whole raised to the power 1 over t. Okay, and then show that fn the sequence, okay, sequence of functions in C01 defined as fnt is equal to 1 minus nt when t lies between 0 and 1 over n, and it is equal to 0 when t lies between 1 over n and 1. So this is a Cauchy sequence with respect to this metric, but not Cauchy sequence with respect to the max metric or d infinity matrix. So here is we have a sequence, okay, a sequence of functions in C01, and we will have to prove that this sequence is a Cauchy sequence with respect to this metric, but it is not Cauchy with respect to this metric. So here is you can take because you can divide this integral into two parts, in the one from interval 0 to 1 over n, and then from 1 over n to 1. Okay, so and then you can put it the value. So f of t in this interval, okay, it is equal to is this, in this interval it is equal to this one. So 0 to 1 over 2, you have 1 minus nt. So 1 minus nt, so and then f m minus 1 minus mt. So m 1 is cancelled, you will get m minus nt square and t square dt. And the other you will get it is 0 and 1 minus nt square, and then you take this whole square. Okay. So this must be equal to 1 over 2. This is 1 over 2, not whole square. This is 1 over 2. So it is equal to, if you will solve it, you will get this one. Okay. So this is what? This means that if you take mn tends to infinity, this will tends to 0, and therefore the sequence fn is a Cauchy sequence. But if you consider the d infinity or max metric, which is defined in this way, then it is equal to 1 minus 1 over m. And now you can show that this is not a Cauchy sequence. Okay, this may not converge to 0 as mn tends to infinity. So here you will get infinity by infinity form. So here you can see that a sequence can be a Cauchy sequence with respect to one metric, but not with respect to other metric. Okay. So this you can remember as an example to show that in a metric space, a sequence is Cauchy with respect to one metric, but not Cauchy with respect to the other metric. So that is the means I finish over here about the Cauchy sequence and several exercises on Cauchy sequence and the relation between Cauchy sequence and convergent sequence. Now we come to the next section, that is complete metric space. Okay. Now, so what is complete metric space? As we have seen that every convergent sequence is a Cauchy sequence. Every convergent sequence is a Cauchy sequence. But every Cauchy sequence need not be convergent in the underlying space. Okay, we have seen several examples where we have seen that the sequence is a Cauchy sequence, but it is not converging to a point in the set. Okay, so it, of course, it is holds good in R. It is true in R because the Cauchy criteria holds good in the set of all real numbers, which you have studied in the course of real analysis. But it is not true in the case of general metric space. So if every Cauchy sequence is convergent in a metric space, then that metric space is called a complete metric space. So the definition of the complete metric space is a metric space XD is said to be complete if every Cauchy sequence in X converges to a point in X. This is very important, converging to a point in X. Okay. So every Cauchy sequence in X converges to a point in X. Now keep in mind, when we consider XD, so there is a possibility that a metric space having one or two matrices, okay, a sequence is Cauchy with respect to one metric and converges to a point in X with respect to the same metric, but it is Cauchy with respect to some other metric, but does not converge with respect to that second metric. Okay, so here is you can see that in the light of the theorem 2.23, a metric space XD is complete, okay, if and only if every Cauchy sequence in X has a convergent subsequence. So we can say that a metric space X is complete if and only if every Cauchy sequence in X has a convergent subsequence. Let us take some examples. Okay, so first we have to consider the example, the set of all real numbers or set of all complex numbers. So we know that a set of all real numbers and complex numbers. So for set of all real numbers, we have the Cauchy criteria, which you have studied in your course real analysis, where you have proved that a sequence is convergent if and only if it satisfies the Cauchy criteria. In other words, a sequence Xn in R is convergent if and only if it is a Cauchy sequence. So the first is you can prove from your old. But let us prove this is here. How we can prove this one? So then let us take here is the second is the set of integers with the usual metric space is a complete metric space. Okay, set of integers with respect to the usual metric space dxy is equal to mod of x minus y. So let us prove this one. Okay, so first part you have already proved in the course of real analysis, so I am not going to give this proof here, but here you can prove the B part. So let us verify the B part. So the verification for B part is let Xn be a Cauchy sequence of integers. Okay, Cauchy sequence of integers, that is each term of the sequence belongs to this set Z, which is in this set. Okay, so each term of the sequence is integers. Then the sequence must be of this form x1, x2, x3, xn and then xxn. Why it is so? Look here is because xn is a Cauchy sequence. Keep in mind. Okay, Cauchy sequence of integers. Then the claim is that the sequence must be of this form. Why it is so? Because indeed we can choose epsilon is equal to 1 over 2. Then for xn and xm in Z, for xn and xm with integers, the mod of xn minus xm is less than epsilon by 2. If the difference between these two is less than epsilon by 2 because it is the integer. So the difference it should be 1 if they are different. Okay, if they are not difference is less than 1, so they must be same. So it means that the xn and xm here is this is less than epsilon by 2. So it means that because xn and xm are integers and the difference is less than half, so they must be same. So xm must be equal to xm. Hence the sequence after some positive integer n, capital N, the sequence must be of this form. So it is what? It is a eventually constant sequence and which will converge to the point x. Okay, and therefore you can consider every Cauchy sequence in Cauchy sequence of integers. Okay, or you can say every Cauchy sequence in the set of integers is a complete metric space, or every Cauchy sequence in a set of integers is convergent, and hence Z set of integers is complete. So that is the way to prove that. Now we take another example. So to consider another example, here is let us take the Euclidean space Rn with the usual metric. Okay, this you have seen, this is the usual metric dxy is equal to this. This is the usual metric. Okay, Euclidean space with the usual metric is this one. Okay, now we claim that the Euclidean space Rn with the usual metric is a complete metric space. That is, every Cauchy sequence in Rn is convergent in Rn. Okay, to verify this one, let us take Xm. Here is Xm. Okay, let M be a Cauchy sequence in Rn, where this is what? This is your X, this is a sequence. Okay, so the term Xm, okay, Xm term of this sequence must be of this form, because the element of this are n tuples, x1, x2, xn. So they must be like x1m, x2m, and so on, xnm. Okay, and say for that is to say the first term of the sequence is x1. So it must be of this form: x1 1, x2 1, and so on, xn 1. Second term of the sequence is x1 2, x2 2, xn 2, and so on. Okay, so the mth term of the sequence of this form. Okay, and now this sequence is a Cauchy sequence. Then for each epsilon positive, there exists a positive integer n such that dxm, okay, and xp, dxm and xp is equal to, here you can take because this is equal to k. Okay, so summation k runs from 1 to n. So this must be xkm, xkp for all mp is greater than capital N. Now we can square both the sides. So we can take this is less than epsilon. So we will have the square of this. Okay, this is less than epsilon square. So this is less than epsilon square. So the sum. So all the sums are less than epsilon square. It means that each term, okay, because this is the square, so cannot be negative. So each term is less than epsilon square. So this is less than epsilon square. But this is what? The xkm, xkp, they are what? They are real numbers. Because they are real numbers. So they are real numbers. They are real numbers. So this is real number. So this means mod of xm minus xk mod is less than epsilon. It means what? It means that xmp or xm, xkm is a sequence, is a Cauchy sequence of real numbers. Okay? In other words, you can say that xkm is a Cauchy sequence in the usual metric space R. And we have seen that R is complete, and therefore xkm converges to some point in R. Say xkm converges to xk. Okay, for each k runs from 1 to n. So it means that x1m converges to x1, x2m converges to x2, xn m converges to xn, and this way we can form a sequence. So we can form a point, okay, such that this is what. So let us take x is equal to the component, these component x1, x2, xn. Then clearly x is in Rn, and we can see that dxm x is equal to this by the definition. But each this, okay, this converges to 0, and therefore the whole thing, this converges to 0. It means that this is a convergent sequence which converges to the point x, and thus xm is convergent, and hence Rn is complete. In the same way, one can prove that unitary space Cn is a complete metric space. Now, in the exercise 2.22, by exercise 2.22, every Cauchy sequence is convergent in a discrete metric space. Every Cauchy sequence is convergent in a discrete metric space. Hence, every discrete metric space is complete. So, if we are considering completeness of a metric space with respect to the discrete metric, it is always complete. So, here is completeness. So I stop over here and we will continue to examine several other examples of complete metric spaces. So thank you very much.